Welcome everybody to the 9th Isfahan Seminar on Representation of Algebra. It's a great pleasure for me to introduce the first speaker, Professor Osamu Iyama from University of Tokyo. He will speak on Cohen-Macaulay representations of Artin-Schelter Gorenstein algebras of dimension 1. Yeah, please go ahead.
Okay, so thank you very much for inviting me for this online seminar. And yes, today I will talk about Cohen-Macaulay representation of certain non-commutative Gorenstein ring, which is called Artin-Schelter Gorenstein. And today I will concentrate on dimension 1. And all result in this talk is from joint work with Yuta Kimura and Kenta Ueyama. And this work is already on archive. And let me start with, origin of our talk. Yes, actually, this work is a non-commutative version of my previous work, joint work with Ragnar Bookbites and myself and Kota Yamaura. Yeah. This work was published in 2000, I think 20. Yes, 22. Yes, maybe I'm wrong. Anyway, it is published from Forum Mass Sigma. And yes, in this work, we study Cohen-Macaulay representation of commutative Gorenstein ring. And yes, today what we explain is its non-commutative version. Yes, and actually this seminar is devoted to the memory of, dedicated to the memory of Ragnar Bookbites. And yes, I'm very happy to talk about this joint work with him. So let me start with the main object of this talk. So for this, I let A be a Neitarian ring. Yes, and I don't assume commutativity. So this is a Neitarian ring. And in this case, the singularity category was also called the stable derived category of A by Ragnar Bookbites is defined as the Verdier quotient of bounded derived category of finitely generated A modules, modulo all perfect complexes. It is just a bounded homotopy category of finitely generated projective module. So this was originally introduced by Ragnar Bookbites in his famous lecture note in 1987, which is recently published, and also introduced by Orloff from global geometry version in the context of mirror symmetry in this century. And yes, actually, in this talk, or yes, most cases, the study of singularity category is given for special case of Neitarian ring called Gorenstein ring, or sometimes also called Iwanaga Gorenstein ring. So I assume A is Gorenstein, or Iwanaga Gorenstein. And this just means that the meaning of Gorenstein ring is as usual for commutative ring theory or local case, equivalent to that the injective dimension of A over itself is finite on both sides. Yes. And under this assumption, the singularity category behave much nicer than non-Gorenstein case. The main reason is that there is a very nice class of A modules called Cohen-Macaulay modules defined as follows. And it gives an enhancement of singularity category. So Cohen-Macaulay module is defined by vanishing of positive extension group from X to A. Yeah. And then this forms a Frobenius category. Yes, so this is an extension closed subcategory of finitely generated A modules, and the relative projectives and relative injectives coincide. Yeah, relative projective, of course, coincide with usual projectives, and it is injective in this category. Yeah, and moreover, it has enough projective object and enough injective objects. Moreover, as I said before, the stable category of Cohen-Macaulay A module is canonically equivalent to the singularity category of A. So, in this sense, this Frobenius category gives an enhancement of singularity category. Yeah. So therefore singularity category is have morphism set in singularity category is yes not very large. If A is commutative Gorenstein, then it is finitely generated R module for A module, for example. Yeah. And yes, today, yes, I will discuss property of singularity category of yes, Artin-Schelter Gorenstein algebra. Yeah. And before talking about this, let me, yes, actually, this viewpoint, singularity category is equivalent to the stable category, and it forms a triangulated category. This viewpoint is, this point of view is very, very, very useful to study Cohen-Macaulay representation. Yeah. Let me talk about, let me explain, let me give a typical prototype example. It is given by ADE singularity, singularity of type ADE. Or it is often called the simple singularity. And I took only the case of dimension 2, yeah, for simplicity. In this case, the singularity category of R is, yes, this is yes, equivalent to so-called cluster category of path algebra of Dinkin quiver Q. Here, yes, Q is Dinkin quiver of the corresponding type, yes, ADE type. Yes, and KQ is just a path algebra, and one cluster category is defined by taking orbit category of perfect derived category modulo Auslander-Leiten translation. Yeah, and yeah, this is very well-known category in representation theory, and this equivalence is, of course, originally due to Auslander and Leiten, but in last century there is no cluster category, and this statement was justified, can be justified by work of Amio, for example. Yeah. And yes, so yes, somehow using Dinkin quiver, we can describe singularity category very nicely. Yeah. So this is some motivation of our work. So yes. So basically, yes, using representation theory of a finite dimensional algebra, we get information on singularity category of, in general, very difficult Gorenstein or non-commutative Gorenstein ring. So this is our motivation. Yes. And yes, before explaining what is Artin-Schelter Gorenstein, let me talk a little bit variation of the setting above. So now I assume A has Z grading. So A is G-graded Noetherian ring. In this case, we can define G-graded singularity category by in the same way. Just replace replace mode A by the category of G-graded finitely generated A module and project A by G-graded finitely generated projective Z module. Yes. Then we have basically same description of G-graded singularity category by using G-graded Cohen-Macaulay module. Yeah. Of course, G-graded Cohen-Macaulay module is defined by just, yes, they are precisely G-graded finitely generated A module satisfying same vanishing condition. Yes. Then, yes, then actually this example, ADE example has G-graded analog namely G-graded singularity category of ADE singularity is equivalent to the perfect derived category of Dinkin quiver. Yeah, there is natural Z grading on ADE in singularity. And this equivalence is already somehow appear in work of Geigler and Lenzing in their work on weighted projective line in last century. And also, yes, and this statement is explicitly stated in work of Kajiura, Saito, and Takahashi in this century. Yeah. So remember that, yes, Dinkin quivers are precisely representation of finite quiver by Gabriel's theorem. On the other hand, ADE singularity are precisely representation of finite Gorenstein ring, commutative Gorenstein ring by work of yes, Groyer, Schreier, and Bookbites, Groyer, Schreier, and Knera in last century. Yeah, so somehow, yes, so using singularity category and Cohen-Macaulay representation, so two commutative representation theory and quiver representation theory can be directly related in this way. Okay, so this is general background. Then let me pose a very general and also very difficult question in general. The question is very simple. So when does the triangulated category of graded, so assume that we have G-graded Gorenstein ring. Yes, oh, I forgot to write G-graded here. So assume that A is G-graded Gorenstein. Then when the stable category of G-graded Cohen-Macaulay module admits a tilting object. Yes. So what is a tilting object? So tilting object is basic to study the equivalence of derived category and also triangulated category. And the definition is very simple. So now I denote by T the stable category, then this is a triangulated category as I mentioned. Then an object U in T is called the tilting object if it satisfies the following two conditions. So first condition is X-vanishing condition. So there's no homomorphism in T from U to any shift of U for non-zero integer I. So I is any integer except for 0. Then the other condition is a generator condition, namely as a sixth subcategory, T is generated by U. So sixth subcategory is a full triangulated subcategory of T closed under taking mapping cone and suspension and inverse suspension and also direct summons. Yes. So these two conditions can be regarded as a triangulated analog of the classical notion of progenerator in Morita theory. Yeah. So this is a kind of asking Morita type theory for stable category of Cohen-Macaulay module. Yeah. Anyway, so this is a motivating question. And yes, there are many known results on about this question, this problem. But yes, I omit to list up results to save time. Yeah. So today, yes, we study this general question for Artin-Schelter. So we study this problem for Artin-Schelter Gorenstein ring of dimension 1. So let me start with what is Artin-Schelter Gorenstein algebra. So definition comes. Yes. So now we consider a G-graded ring A, and I denote by degree I part by AI as usual. And I assume that, yes, negative degree are 0. Yes. And I assume that this is Neitarian. Yes, for simplicity. Yes. So we assume this is Neitarian, and this is also K algebra. So algebra over field K. Yes. And this such an algebra is called Artin Artin-Schelter Gorenstein algebra if the following condition is satisfied. Yes. The condition is mostly analog of the property or definition of commutative Gorenstein ring. Yes, but let me restart. So dimension D, yes. So first condition, yes. So first condition is this is Gorenstein in the following sense. Namely, as I denote above, okay, yes. Injective dimension of A is finite. So this is the meaning of Gorenstein. And here, yes, when we say A has dimension D, then injective dimension is precisely D on both sides. Yes. So this is the first condition. Yes. But yes, people who know non-commutative ring somehow know that just finiteness of global dimension or finiteness of injective dimension, self-injective dimension are usually not very strong condition. Yeah. As comparing to nice property of commutative regular ring or Gorenstein ring. So to get such nice property like in commutative setting, we need to assume so-called Gorenstein condition. Yes, too many Gorenstein. Yeah. Anyway, the condition, second condition is very simple, also simple. Namely, for any simple A module, sorry, yeah, any simple A module, and assume that this is graded module. And moreover, it is concentrated in degree zero. Namely, degree zero part of S is just yes, non-zero degree is zero. And then consider the extension group from S to A. Yes. Then this extension group, so yes, when I say module, it is, I mean, right module. Then taking extension to A, then it becomes a left module. Yes. Then this left A module, x to I S A, this is mostly zero. Yes. So if I is actually not equal to D, then this x group vanish. Then let's look at the degree, I equal D. Yes. So then this extension group is actually again simple module on opposite side. Yes. So x to D from S to A becomes again simple A module. Yes. So this is a condition. Yes. And moreover, yes. So this must be concentrated in some degree. And I denoted by, yes, the degree concentrated, yes, this module concentrates by PS. Yes. So I did not highlight concentrated in degree, some degree, and I denote this degree by minus PS. Yes. Yes. So this minus sign is just a convention. Yes. And anyway, yes, point is x to D from S to A is concentrated in 1 degree. And yes, these two properties are yes, satisfied by graded commutative Gorenstein ring. Yes. And let me add third condition. So third condition is just very technical. Namely, yes, each degree of A is finite dimensional over base field K. Yeah. So so K is always a field. Yes, in this talk. So algebra, graded algebra satisfying these three conditions are called Artin-Schelter Gorenstein algebra. Yeah. Remark that just a minor small remark is that often in the definition of Artin-Schelter Gorenstein ring, it is assumed that degree zero part of A is K. Yeah, but yes, as you know, yes, yes, important point of non-commutative ring is there are many idempotents. Therefore, yes, to study non-commutative ring, it is very natural to assume, not assume degree zero part is K. So we don't assume this. Yeah. Then let me talk a bit about example. So yes, as I said before, commutative graded Gorenstein ring are example of Artin-Schelter Gorenstein ring. Yeah, more precisely, yes, if degree zero part is yes, if degree zero part is filled, yeah, then this condition are satisfied. Yes. And let me just show you some table. Yes, actually there is a very nice, important hierarchy of non-commutative ring. Yes, I wanted to cut and paste. Yes, did I copy? Yes, I see. Yes. Yes, so yes, to save time, I'm sorry, I just to save time, I cut and paste this. Not very good. Maybe this is too big. Sorry. Yes, please accept, please accept, yes, this figure. Yes, yes. This commutative side is left and non-commutative one is right. Anyway, yes, so you see, yes, so here, this is a frequently studied class of non-commutative Gorenstein ring or subclass of Artin-Schelter Gorenstein ring. Yeah. So here our Artin-Schelter Gorenstein algebra appear here. Maybe I should make a bit big. Okay. Okay. Yes. How to make bigger. Sorry. Yes. Yes, slightly. Yes, let's concentrate on this. Yes, so now AS Gorenstein algebra here, and there are more well-studied class of Artin-Schelter regular algebra. And Artin-Schelter regular algebras are defined just by replacing first condition by global dimension equal D. And yes, second condition are still same. Yes. And yes, actually, it is well known that Artin-Schelter regular algebras are graded and twisted version of so-called Calabi-Yau algebra. Yes, introduced by Ginzburg, and differential graded version are very deeply studied by Keller and their school. Yes, and there's a class so-called singular Calabi-Yau algebra. This is just dropping homologically smoothness from definition of Calabi-Yau algebra. Yeah. So there's yes, and the singular Calabi-Yau algebras are just a non-untwisted version of our Artin-Schelter Gorenstein. And maybe I will talk more about, yes, actually there are more classical class of non-commutative Gorenstein ring, so-called Gorenstein order. Yes, there are many books, let's say Curtis Reiner's famous book. Yes, there are many study of representation theory of Gorenstein order. And these subclass have some corresponding class. Yeah, but yes, and because my time is limited, let's go to the to explain our theory. Yes. So now, yes, we will give talk about existence of tilting object in singularity category. But or singularity category is equivalent to the stable category of Cohen-Macaulay. But yes, actually, we slightly modify the category of stable category of Cohen-Macaulay module in the following way. And to explain this modification, I need to introduce the category Q group, which is one of central object in so-called non-commutative algebraic geometry. Yeah. So this Q-group category is just a cell quotient of the abelian category of G-graded finitely generated A modules modulo G-graded finite dimensional A modules. Yeah. So of course, this is analog of the category of coherent sheaves over projective scheme given by graded commutative ring. Yeah. And yes, using this category, the aim to introduce this category have several meaning, but from our point theorem, what is important is to give the total quotient ring of A. Yeah, we can define total quotient ring, total graded analog of total quotient ring of A by the following equality. So consider this abelian category Q A, then take the morphism space from A to degree I shift of A. Yeah. So yes, degree, yes, I always denote by bracket I, this circle bracket I, the automorphism of the category of graded A module, which induces automorphism of Q group A. And in this way, yes, using in this way, we can define graded version of total quotient ring of A. And using this quotient ring, we define the category CM0A nodes and graded CM0A as follows. So this is a full subcategory of the category of G-graded Cohen-Macaulay A module, satisfying the following condition. Namely, yes, so taking a tensor product with Q, it becomes projective. Yes, yeah, projective over Q. Yes, this is a definition of CM0A. Yeah, yes. Yeah, actually, this definition, yes. So this definition is somehow special, special for the case D equal 1. Yes, D is the dimension of Artin-Schelter Gorenstein algebra. Yeah, yes. And yes, in higher dimension case, the category CM0A becomes, definition becomes more complicated. Anyway, then let me explain a few properties of yes this category CM0A. Yes, actually, yes, this type of restriction of Cohen-Macaulay modules to this CM0 category, this is very classical in Auslander-Leiten, so-called Auslander-Leiten theory. And actually, some of, yes, one of property is that, yes, in this case, our category CM0A has almost split sequences. Yes, actually, this existence of almost split sequences is not hold in general in for category CMA. Yeah, so this CM category A usually does not have almost split sequence. But if we restrict to this subcategory, it has almost split sequence. Yeah. In particular, the stable category has cell functor, and the cell functor is given by canonical module. Yeah, but yes, I omit such details. Yes. So now, yes, I want to state our main theorem. Yeah. So for this, let A be, well, again, yes, let A be Artin-Schelter Gorenstein algebra. Yeah. Okay. Maybe copy and paste is maybe not very good for, oh, no, it doesn't work. I don't know why. Sorry. Yes, maybe I should write. Then let A be Artin-Schelter Gorenstein ring. So AS Gorenstein by abbreviation. And moreover, I assume that this is dimension 1. Yes. And then we have a Gorenstein condition. So simple module is behave very nicely with respect to A dual. Yes. Then yes, because yes, yes, the degree 0 part. So graded simple modules are precisely simple module over the degree 0 part A0 of A. So there are only finitely many simple module, graded simple module concentrated in degree 0. And I denote them by S1 to Sn. So they are simple A modules concentrated in degree 0. Then they have okay. Yes, as I said before, then there is yes. So taking extension group, it is concentrated in degree minus p. Yes, and so yes, so I forgot to introduce some word. So this minus PS is called, or maybe more precisely speaking, PS is called Gorenstein parameter. And actually, for commutative case or classical Artin-Schelter Gorenstein case, A0 equal K, then there is only one simple module concentrated in degree 0. Yes, but here we have several simple modules concentrated in degree 0. So Gorenstein parameter is given for each simple module. Yes, so this is one important point in our setting. So I denote by P1 to Pn, they are just Gorenstein parameter. Okay. And yes, Gorenstein parameter, the sign of Goren, it is well known that the sign of Gorenstein parameters are, yes, very important to understand the behavior of Gorenstein ring. Yeah. And actually, yes, this is also the case in our theorem. Yeah. So now we are ready to state our main theorem. So yes, I assume that the global dimension of degree 0 part is finite. Yes. And remark that classical case A0 equal K, it is automatically satisfied. Yes. This is just a remark. Then, yes. Then let's talk about the stable category of Cohen-Macaulay model. Yes. Then, yes, this is a triangulated category. Oh, yes, maybe I forgot to remark that this category is, yes, again, Frobenius category. Yes. So this is a full subcategory of four graded Cohen-Macaulay module. It was Frobenius, but this subcategory is also Frobenius. Therefore, its stable category is also still triangulated category. And we ask if this category has a tilting object or not. Yes. And yes, actually, yes, this category does not necessarily has a tilting object, but it still admits a weaker version of tilting object, which is called shilting object. Yes. So shilting object was, yes, originally introduced by Keller-Hoschek in 1987. But yes, in this century, this notion this notion was paid more attention in this century. Yes, thanks to connection to cluster algebra and their mutation theory. Yes, actually, yes, shilting object can be, the definition is very simple. So instead of assuming all extension group vanish except for the 0 degree, shilting object satisfy the vanishing condition that all positive extension vanish. And still same generator condition is satisfied. Yes. So studying shilting object is, yes, maybe, yes, if we are familiar with the notion of differential graded algebra, then yes, shilting objects are nothing but connective differential graded algebra. Connective just means all positive degree vanish. Yes. So studying shilting are precisely studying connective DG algebra and for algebraic triangulated category setting. Yes. Anyway, then, yes, actually, yes, one of our statement is, yes, this stable category always admits a shilting object. So this is our first statement. And moreover, this shilting object can be described very simply, yes. Maybe I denote it by V. Yes, and this is just, yes, obtained as follows. So first consider degree shift of A by I, yes. And then take submodule consisting of non-negative degrees. So we throw away negative degrees and take the all direct sum of those graded A modules. Yes. Yes. So this is our definition. Okay. Remark that yes, actually yes, so this is yes. So each direct summand is graded A module, even Cohen-Macaulay A module. and belonging, which belongs to our category CM0A. And we take direct sum of all of them. Yes. Remark that this is actually infinite direct sum, but actually, so these modules are actually periodic with respect to I. So somehow we don't need a sufficiently large I. So yes, we throw away large I's. Yes. So yes. So the statement is for sufficiently large integer large n, this gives a shielding object in our stable category. Yes. And moreover, actually, second statement is V is actually a tilting object if the following additional condition is satisfied. Namely, the additional condition is stated in terms of Gorenstein parameter P1 to Pn. Yes. Actually, if all of P1 to Pn are non-positive, then our V is actually a tilting object. Yes. So, yes, so if all Pi's are, in particular, if all Pi's are non-positive, then this category has a tilting object. Yes. But actually, existence, this is sufficient for existence of tilting object, but not necessary. And actually, sufficient and necessary condition for existence of tilting object is given as follows. Yes. Actually, there are two cases. Yes. First case is the algebra A is AS regular, in the sense that the global dimension is finite. Yes. So if A has a finite global dimension, then the singularity category is 0, and in particular, this triangulated category is also 0, because it is a full subcategory of G-graded singularity category. Yes. So 0 category, of course, has a 0 tilting object. Yes. So first case is the trivial case. But actually, non-trivial case is the second case. Namely, the second case is that, yes, the sum of Pi's. So just take sum of P1 to Pn. Yes. And this sum is non-positive. Yes. Or maybe, yes, I need to assume that, yes, A is ring indecomposable. Yeah. Yes, of course, assuming ring indecomposability is, well, not very mild condition. Yes. And yes, this just means indecomposable as a ring. Then moreover, I assume global dimension. So finiteness of global dimension is more essential condition. But anyway, yes. So sum of all Gorenstein parameter is non-positive. Yes, this characterizes existence of tilting object. Yes. So this is our means. Yes. And in the rest of my talk, I will explain some example and yes, also some proof, part of proof. Yes. Okay. So now, yes, maybe, yes, not many people are familiar with Artin-Schelter Gorenstein ring, I guess, and therefore, yes, I want to tell you some example. Yes. And yes, actually, main example for me of AS Gorenstein ring is given by so-called classical Gorenstein order. Yes, and it is very simple. Let me try to explain. So let K be a base field, and let's consider let R be a polynomial ring, let's say of D variables. Yes. And assume that, yes, so this is, we consider this is G-graded ring. Yes. And each xi is homogeneous. Yes. Consider such polynomial ring. Yes. Then consider an A algebra A. And assume that, yes, yes, so I assume that A is so-called R order. Yes, maybe this notion may not be well known for people. So let me explain what is Go. Yes, not only R order, but I assume A is Gorenstein R order. Yes. What does this mean? Yes. Yes. This is just in a word, this is just R version of self-finite dimensional self-injective algebra. More precisely speaking, so this A satisfies the following two conditions. So as an R module, A is projective. So this is first condition. And second condition is, yes, taking R dual of A. Yes, because R is, okay, so yes, so I should first say that A is an R algebra. And moreover, satisfying two conditions. So projectivity over R and yes, moreover, taking R dual, it becomes again A module. So A is A by module, and taking R dual, it is still A module. And regarding this as right A module, it is projective. So this second condition is Gorenstein property. First property is R order. Yeah, okay. And moreover, I assume that A is still graded ring. Yes, non-negatively graded ring. G-graded ring, which is this degree is compatible with grading of R. Yeah, compatible with R grading. G grade. Okay, yeah, this is actually not very essential. So A is just G grade. So assume that these two conditions are satisfied, then actually A is Artin-Schelter Gorenstein ring algebra. Artin-Schelter Gorenstein algebra of dimension D. Yes. I need to assume that yes, each degree of each xi is positive. Yes. Then yes, A satisfy all three conditions. Yeah. And moreover, in this case, the Cohen-Macaulay graded Cohen-Macaulay modules over A are precisely graded A modules such that X is projective as R module. Yes. So Cohen-Macaulayness is base essentially means projectivity over base regularing. Yeah. So this is yes, important point. Anyway. So now, yes, I have 5 minutes remaining. So I need to give a more concrete example. Yeah. So this is very well. This looks maybe yes. This looks still very abstract, but actually there are easy, very many easy and fun. Yes, important example. So consider just dimension one case. So R is a polynomial ring of one variable with standard grading, and M is maximal ideal, graded maximal ideal of R. Then consider A of this form. R, and here MA and MA's power of A, maximal ideal A. So A is positive integer. So this is a subring of 2 by 2 full matrix ring over R, and this is actually Gorenstein order. It is yes, order of this form. So subring of full matrix ring over R, and each entry is certain power of graded maximal ideal. Such an R order is called tiled order, and this satisfies Gorenstein property. So this is actually Gorenstein tiled order. Yes, and yes, actually yes. This is actually so. In particular, this is Gorenstein order. So this is AS Gorenstein. Yes, and maybe yes, yes. Let me explain. Yes, yes. Let me explain briefly the representation theory of this order. Yes, actually, the indecomposable object of this is actually so special case of so-called bus order. studied by Bas and Kiev School, Drozd, Kirichenko, Reuter, and so this is a very special case of this. And for example, there are only finitely many maximal indecomposable objects in our category CMZ. And it is given by the following list. Yes, actually, it is all indecomposable Cohen-Macaulay models are just given by row vector, and I and j satisfies this inequality. I and j are possible integer satisfying this inequality. Yes, and yes, actually this case, maybe yes, to save time, let me cut and paste Auslander right quiver I prepared. Sorry for this. Yes. Yes, actually, this is part of Auslander right and quiver of this category graded Cohen-Macaulay modules. Yes. Yes, actually, yes. Actually, this is a very typical ZA2A plus, precisely speaking, Z2A plus 1 quiver. Yes. So this is the translation quiver. So tau is in this direction. Yes. So here we have a quiver of type A to A plus 1. Yes. And yes, so this is actually part of Auslander right and quiver of this category. Yes. And yes, so because each indecomposable modules are parameterized by two integer I and j, so I just denote this by ij. So every vertex are given by pair of two integers. Yes. Yeah. And then in this case, actually our condition is satisfied. And actually, yes, actually we have, yes, actually this case, maybe yes, I should say. So there are two simple modules, K0 and 0K. And actually Gorenstein parameter of them are actually given by 1 minus a. Yeah, one can easily check it is 1 minus a. So in particular, they are non-positive. Therefore, we have a tilting object V. It is given by degree shift of, non-negative part of i's degree shift of A. Yes. And actually, yes, in this case, yes, one can easily check that, yes, these modules are precisely modules given by this blue section. Yes. And you see, yes, so this is yes, this is the thinking quiver. Yes. And yes, so we have ZA to A plus 1 quiver, and remember, yes, important point is top row and bottom row are projective injective. So taking a stable category, we get Z2A minus 1. So stable part is just Z2A minus 1. So in particular, yes, we get a quiver of ZK2A minus 1. And our main theorem implies that the stable category of graded Cohen-Macaulay module is equivalent to the perfect derived category of thinking quiver of, yes, this type 2A minus 1. Yeah. Yes. So this is actually very simple. Yes. Just a thinking picture. Yes. But actually there are many, yes, many examples we can apply our theorem. And maybe, yes, let me cut and paste one picture. Sorry for this. Yes, writing down picture takes some time, so let me save time. So this is just still tiled order, but yes, 4 by 4 now. Yes, and yes, this is yes. So R is still polynomial ring of one variable. Oh, sorry, A. This is A, and R is polynomial ring of one variable. Then, in this case, this is still Gorenstein tiled order, and yes, actually, this case we can still apply our main theorem. Actually, each Gorenstein parameter are non-negative, and yes, actually. Yes, endomorphism algebra of our tilting object is incidence algebra of this poset. Yeah. So this is actually has a quiver of certain poset. And for tiled order case, actually, yes, our algebra, endomorphism algebra of V is always incidence algebra of a certain poset. Yeah. And yes, this case, the poset is like this. Yeah, we have n by n version of this, but I omit, yes. And there is also other application for non-commutative, non-commutative quadric hypersurface. Yeah. So it is, yes, there is some nice family. So non-commutative quadric hypersurface. This is actually nice class of Artin-Schelter Gorenstein ring, and by using Kossel duality, we can reduce the study of the category Q coherent sheave over Q by using its Kossel dual. Yes, and actually Kossel dual of B is actually still AS Gorenstein algebra, but dimension becomes Gorenstein algebra of dimension 1. Yes. Somehow, yes, hypersurface is projective resolution of hypersurface is periodic, and this periodicity is reflected to this dimension 1 property. And by Kossel duality, by usual one and modified version by Isle-Mori, we have such category duality, and yes, in particular, this this category has a tilting object. Yeah, but I omit some detail, and yes. Yes, so there are some examples. Yes, and yes, I'm sorry, I have to omit the proof, but proof is not also very difficult, and yes, I recommend to look at our paper. It's very simple. So thank you very much for your attention.
Thank you very much for your nice talk. Yes, there are some questions. Please.
Sorry, I clicked the wrong button.
Oh, okay. Are there any questions, comments?
Sorry, I have a very small question here. Could you go back to the picture that you pasted firstly?
This one.
No, the first picture that you
Oh,
pasted.
you mean, oh, this
Yeah,
one?
this one. Yeah.
Okay.
So what is the analog of the left-hand side and the right-hand side?
Yes, they are basically, yes, different, yes, but yes, there are many overlap, very analogous, yes. So, yes, Artin-Schelter algebra are G-graded, yes, so, but orders are usually not G-graded. But if we assume orders are G-graded, then, yes, Gorenstein graded orders are example of AS Gorenstein algebra, yes. So orders is a typical example of AS Gorenstein algebra. Yeah. This is fact.
Okay.
Yes, and there are also this. Yeah.
Okay, so actually right-hand side, left-hand side is the grading version of right-hand side.
Calabi-Yau algebras are not graded also. Yeah, it is DG algebra, but not graded in the sense of Artin-Schelter.
Okay,
So,
so
yes,
Calabi-Yau
Adams
algebra.
grading, yes. So there is also, yes, for Calabi-Yau context, sometimes, yes, we study Calabi-Yau DG algebra with additional Z grading. Yes. And such one, yes, so Calabi-Yau DG algebra with additional Z grading, and moreover, concentrated on degree 0. It is Calabi-Yau graded Calabi-Yau algebra, and it is untwisted version of Artin-Schelter regular algebra. Yeah. I don't say anything deep. Yes. This is just immediate from definition. Yeah.
Okay, so the analog of Calabi algebras and symmetric regular orders is differ by grading.
Differ by grading, and also, yes, we need to assume, so yes, it also depends on base ring. So if base ring is finitely generated over a field, then all symmetric regular orders are Calabi-Yau. Yes.
Okay. Thank you very much.
Yes, already written in first paper by Ginsburg. Yeah. But
Okay.
you can see, for example, my paper with Eden. Yeah. We discuss connection between Calabi-Yau algebras and regular orders, classical notion of regular order due to Auslander. Yeah.
Okay, thank you.
I have a question. So, I have a question. So, in your last three examples, you used the existence of tilting object to say that this Cohen-Macaulay stable category was derived equivalent to the category of perfect complexes. So, I think it's something basic, but what are you using there to conclude?
You mean this or
This and even the previous example, you have this
this
stable
one?
category of
This
yes.
one? This
Yes.
one is actually, yes, I should also add one more step, explain one more step, namely, key observation is consider the endomorphism ring of this V. Yes. And then this endomorphism ring turns out to be isomorphic to path algebra of linking quiver. Yeah. More or less, this picture explains this isomorphism. Yeah. So the object V is object V are direct sum of indecomposable objects on this line. Then taking endomorphism ring, you have a quiver of type 2a minus 1.
Yes. Okay.
And yes, actually this equivalence is one of basic property of tilting object. Maybe
Yes.
this is
Yes.
point of your question. In general, yes, sorry, I omit this, yes. So in general, if we have triangulated category has a enhancement by DG category or Frobenius category and admits a tilting object, then that triangulated category is equivalent to the perfect derived category of endomorphism ring of tilting object. So we have a type of Morita theorem. Yeah.
Yes.
And I use this, yes. Thank you
And I
very
had
much.
yes, I had one more question. So, is it possible to put some grading on gentle algebras so that they become this AS Gorenstein?
Oh, first of all, gentle algebra, so you consider finite dimensional gentle algebra, right?
Yes, I have a finite quiver with those.
Okay, yes,
values of
actually, yes. AS Gorenstein algebra of dimension 0, maybe one equality is so Artin-Schelter Gorenstein algebra of dimension 0. They are precisely finite dimensional self-injective graded, G-graded. Yes, or maybe I should say n-graded in the sense that there is no negative degree. So n-graded finite dimensional self-injective algebra A, and moreover, no, just this, yes. So, yes, we have this equality. So, AS Gorenstein of dimension 0 are precisely finite dimensional self-injective algebra. Yes, and also, if AS Gorenstein algebra have a positive dimension, then they are never finite dimensional. Yes. So all AS Gorenstein algebra of positive dimension are infinite dimensional. Yes.
Yes.
Infinite dimensional. So only possible gentle algebra which can be AS Gorenstein are self-injective. Yeah.
It's quite general.
Yeah, not many, not many. Type A tilde with yes, all path of length to 0, maybe. And maybe yes, but yes, if we allow infinite dimensional gentle algebra, then actually most typical example is just path algebra of A tilde quiver. Yes. Actually, this is AS regular algebra of dimension 1.
Oh,
Yes. Actually, this is just a matrix algebra of a polynomial ring of one variable, like R. So upper entry are R and lower entry are maximal ideal. Yeah. So you see, yes. So path algebra of cyclic cleaver are just tiled order, most basic tiled order. Yeah. You can check this isomorphism. Yeah.
Ah,
And this is certainly gentle algebra in, well,
yes.
locals. Yeah. Mm.
Yes. Okay. Thank you.
Are there more questions? Seems that it's not the case. So let's thank Osamu once more. Thank you very much.